So on this one way to look at what we've got in this integral that's left over is that I have a linear numerator and a non-factorable denominator. So when I have that, then I'm going to use this technique of forcing q prime. Another way to say that is that when I have decided that q does not factor and my numerator, my denominator is quadratic and my numerator is linear, then I'm going to separate into kq prime over q and constant over q. That's what that forcing q prime is really about. You just separate this integral into a part that can be done by substitution and the other part that can be done by completing the square. So as usual, we're going to bring everything down along as we go, right? Not losing anything at any step. And then we're going to say, okay, we know here that du is 2x plus 8, and I could not force that to match 4x plus 7. But if I try to match at least the 4x, then what I would do is I would take this du statement and multiply both sides by 2, and I would end up with, nuts, I thought I could rescue that, 2 du equals 4x plus 16 dx. And of course, my du statement should always have a dx on it. All right, so sorry, we had that off screen a little bit. The du equals 2x plus 8 dx. I want to match at least the first term, so I multiply by 2 and get 2 du equals 4x plus 16 dx. So that's just sort of my scratch work, but then that allows me to write this as the integral of, so I know what I want. I want 4x plus 16. So I'm going to put the 4x plus 16 over the x squared plus 8x plus 18. And what I'm going to do is I'm just going to keep that as a separate integral because these two integrals are going to require different techniques. Now I need to have the plus 7 here, but I put a plus 16. So what will compensate for that? Minus 9. So minus the integral of 9 over x squared plus 8x plus 18 dx. And what I should be able to see at this point is if I combine these two integrals, they have the same denominator, they're both integrals, so I would just combine the numerators and I would in fact get this up here. So what I've done is taken my linear over a non-factorable and separated into a du over u and a constant over a non-factorable. Right, that's what this is saying down here. There's a kq prime over q part and a constant over q part. All right, and we treat them each differently. So the kq prime plus q over constant part, I'm going to use substitution. I'm going to use u equals q of x. I'm going to get ln absolute value of u. And on the non-constant part, I'm going to do 1 over x squared plus a squared and use an inverse tangent. All right, so I'm going to treat these two integrals separately, but I'm just going to keep copying everything down, every line. Even though this, like, what is that? Is that some kind of an angle or something? It's a 2. Let's make it look like a 2. All right, over 2 plus x, also a discipline for me. All right, so now I'm going to look at this and say, okay, I already recorded up here that 2 du is equal to 4x plus 16 dx when the u is equal to x squared plus 8x plus 18. So I already have that. So I'm going to go ahead and use it. I'm going to pull the 2 out to the front, and then I'm going to say that this 4x plus 16 dx, I'm replacing with 2 du, and then my denominator I'm replacing with u, so I have integral of du over u. This is what I should always have in that substitution part. All right, and then I have minus. Now this one I'm going to do by a different technique. So I'm going to use completing the square. So what I'm going to do on this one is I'm going to pull the 9 out. So I guess I'm pretty much always pulling these constants out. And then I'm going to have 1 over. I'm going to say, all right, x squared plus 8x. So I want to think if I complete the square, I'm going to do half of 8 is 4 squared, and I get 16. Okay, but I really have 18, so I need a plus 2 to complete that line. And then dx, all right? So I take the 18 split into 16 plus 2. I did that because here I have x plus 4 squared. All right, so now I'm just working down line by line and, working with each part that has something to be done and leaving the parts that don't. So this, there's nothing to be done, so I'm going to leave it. I'm going to leave it. I'm going to keep my 2. Now I can do this integral now. It's ln of absolute value of u. I'm not going to put the plus c yet because I still have an integral, so the plus c is tied up in that integral. Now I'm going to go over here and do this one. So I'm going to say this is equal to the integral of, I'm just going to show the completing the square step, x plus 4 squared plus 2 dx. All right, and then working down some more, 3x squared over 2 plus x. What can I do on this one? I can sub the u back, so that's plus 2 ln absolute value x squared plus 8x plus 18. And then over here, let's see. I guess I'll just observe here that the a, what's the a equal to in this? We're going to use that. 1 over, the integral of 1 over x, of 1 over u squared plus a squared equals 1 over a inverse tangent u over a. All right, that's our integrating formula for this part. All right, that is the constant over q part. We're using this integrating formula. What's our a? What's our a for this? A is the square root of 2, right? That's this number. We need, this number is a squared, so this is square root of 2. All right, so what I'm going to have for this is, and I can actually just write this integral directly now. Once I've got it in the form of 1 over u squared plus a squared, I can just say what the antiderivative is. So I can even keep that 9, and we'll say, all right, it's supposed to be 1 over a, but I've got this 9 here, so when we get 9 over square root 2, that's a 9 right there, right? 9 over square root 2 is our a. And then it's inverse tangent. So remember, it's u over a next, so the u means we're going to put the x plus 4, and the denominator is square root 2 because the denominator is a. So that's just using this formula right here, 1 over a, but we have 9 over a because it's 9 there. Our a is square root 2. Our u is x plus 4. I should have used u's here, but whatever. All right, so there you go. Now I've done the last integral, so now I can put a plus c there. All right. Now, some people will really want to rationalize this denominator, and that's fine. I'm going to say I've done enough, and I refuse to rationalize that denominator, but you can if you want, right? You could even put over here like square root 2 x plus 4 over 2, but is that really better? I don't know. All right, anyway, that is number 4.